Let us start our today's discussion. It's like this. Let us start our discussion with nozzle efficiency itself. Now, do you know that by the in general term, the efficiency itself is defined as the output divided by input itself. Means output for certain for energy, or certain speed, or certain product is divided by the input given by the same product with same speed or same other properties itself. Now we are considering the flow of steam through a nozzle itself, and we are considered convergent, means the cross-section of the model reduces from the beginning to end at the uniform state. Divergent nozzle, which is this cross-section increases from beginning to end, and convergent nozzle, where first a portion of it is convergent and remainder portion of it is being exhausted here. We also discussed the stagnation pressure of the fluid itself. The stagnation pressure means if you know the value, the isentropic stagnation is defined as a state of a fluid, which fluid in motion, which reach. If the fluid in motion, what is the status of the fluid in isentropic stagnation state? It is defined. It is defined as a state which a flowing fluid is reached. When reached, if it is suddenly isentropically brought to rest from its steady flow in a steady flow adiabatic zero work output device. Means a fluid is flowing and this is isentropic stagnation. Process is isentropic, means there is no heat transfer takes place, entropy is not changing, so heat is also not heat content what it was initially, that more or less remains same, and heat content or enthalpy H was more or less remains same, is supposed to for isentropic concentration. Here we want to by isentropic stagnation means a certain flowing fluid with a known incoming enthalpy and speed is suddenly brought to rest by the adiabatically and in a steady flow adiabatic and zero work output device. Means there should not be no work is created. It is totally adiabatic. Adiabatic becomes it is not losing any heat transfer takes place in the out from the fluid to outside world itself, and still flow is steady, means it is maintaining a steady velocity itself. So what is the condition? What is the state of the fluid if a flowing fluid is brought to rest in a device which is isentropic? First of all, means no heat transfer takes place. Adiabatic, that's also same. No heat transfer takes place, and the flow is steady. There is no change in velocity also takes place, and there is no work is required or is supposed to be done by the output itself. Here, the stagnation pressure, which is when the fluid is stagnated, the pressure, it is a reference state itself in compressive fluid flow completely designated with the subscript 0. It is a reference state. From this state, say H0, the terms means enthalpy at the stagnation, T0 is the temperature at the stagnation, like this. And we are now the stagnation enthalpy or stagnation temperature is now related to the enthalpy on the velocity of the moving air itself. So we are just assuming that the velocity or the flowing fluid, when it is steadily flowing, is brought to rest in air by some artificial means, but without doing any work or without any heat transfer. And then what will happen if it starts flowing again from the remainder part of the flow itself? Means convergent the flow is convergent at a certain point, and up to a certain point it is again divergent. That point which is where with the cross-section is minimum is known as the throat of the nozzle itself, and we assume that the possibly the fluid at this nozzle is at stagnation phase. When it said it is here, it is brought to rest because it is suddenly dropped. The area is dropped to considerable from the inlet to the outlet itself. Now, there is also another, whatever you say, isentropic or adiabatic, but there must be some friction between the fluid and the walls of the nozzle itself. The expansion process is irreversible, although it's still approximately adiabatic itself. Just 1 second. Oh, stop steering much. Recording church. Now, due to the expansion process is reversible, what you say, but there is a friction, as we are considering some actual condition. Say a fluid is flowing in a say converted divergent nozzle, but whatever whatever polish the full surface of the nozzle itself, there must be some friction exists between the fluid and the nozzle walls of the nozzle. That the expansion process is said to be irreversible but not reversible, means it cannot go back to the original stage because certain power is being lost due to friction between the wall and the fluid, and it cannot be recovered at all. Although still we are saying it is approximately adiabatic, means approximately negligible amount of heat transfer takes place in the fluid itself. In nozzle design, you know, the usual practice is to base all calculation on isentropic flow. In nozzle design, the usual practice is to base all calculation on isentropic flow and then to make an allowance for friction or use a coefficient or efficiency itself. So we are thinking of taking into consideration of the certain loss in the enthalpy or energy in the fluid itself, and thus we are taking into consideration of this fall, and we are make an allowance for this fall, for this friction by taking into consideration of a coefficient or efficiency itself. Thus, the efficiency of a flowing fluid is taken into account by in order to take into account what is the amount of energy loss the fluid will face due to its friction between its flowing fluid and its walls of the fluid itself. So that nozzle efficiency is defined as the actual enthalpy drop due to the isentropic enthalpy. Hence, eta n is the nozzle efficiency, is a suffix, is given as n because as for nozzle, H0 suffix 0 is given for stagnation enthalpy, H1 is the enthalpy at the outlet of the nozzle itself. When the actual process is moving actually, and that divided by the H0 minus H1s, which is H0 is of course stagnation enthalpy, and H1 is if the total process is isentropic, what will be the energy itself? This isentropic energy output energy is definitely much higher than the actual energy because there is no heat loss takes place in isentropic heat flow, and this energy is dropping from H0 to H1 considerably due to the friction itself. So for an ideal gas, efficiency N, efficiency with the suffix N is equal to Cp, means C to the suffix P is equal to T0, T to the suffix 0 minus T1, T to the suffix 1 and divided by Cp or the specific heat at constant pressure and the specific heat at constant pressure and T0 temperature at the stagnation point, and T1 is temperature at the outlet, and T0 temperature at the stagnation point, and TIS is the temperature, isentropic temperature. Which if there is no friction takes place, this will be the temperature itself. But the temperature T1 is much less than TIS because due to the frictional flow friction output, this T1 is constantly reduced. It can be caused here. Here, a lot of heat is lost during the high-speed flow of the nozzle itself, or it is reduced to T0 into minus T1 divided by T0 minus T1s. So, what in an enthalpy entropy chart, it ordinary TS diagram in a molecular polymer diagram, what we find is at the abscissa we plotted the entropy change in entropy, and at the ordinate we change in enthalpy itself. So we have plotted, find out from the chart itself the two pressure, that is P0 equal to the stagnation pressure, P1, which is the outlet pressure. P1 must be less than P0 because due to flow of energy, this pressure falls and velocity also increases considerably. So we have a curve, is another graph is drawn about this is the stagnation pressure P0, and this is the stagnation temperature T0, which is plotted in the curve, where the stagnation pressure intersect the stagnation temperature. We got a point O, it is a stagnation point. This, which is a common point, is a point where we got the enthalpy and the entropy, and entropy, which is our stagnation point itself. So first we plot this, find out this P01 from the diagram, the molecular diagram itself, then P1 diagram, and this curve is here, and we put the curve of the temperature T0, and in the intersection we got the point 0 or the stagnation point. If we drop a particle, it will reach the pressure P1, means outlet pressure at 1s, which is the entropy given. Here we show that this is the process. Actual there is no entropy losses takes place, but actual process where the entropy is going here, because there is some entropy rises to a certain extent, and to a certain extent enthalpy also changes, but not that extent itself. Means entropy goes out, means there is a considerable amount of heat is being lost from 1 is to 1. The actual velocity at the exit from the nozzle is V1, and the velocity at the exit where the nozzle is isentropic is V1 dash itself. So for next, we are going to the velocity. We are interested to know the velocity because we want to impeach the stream at high temperature on the blade of the nozzle itself. The actual velocity at the exit for the nozzle is V1, and the pressure at the exit when the flow is isentropic is equal to V1s. So we are getting two velocity now from the nozzle. When actual velocity is V1, which means there is some friction, the velocity cannot be that high, and there is no friction, there is no energy loss due to isentropic. As the process is isentropic, then V1 dash exists. V1 dash is much more than the V1 itself. V1s is much more than V1 itself. Then stagnation, so we are subtracting the V1 square minus V0 square, means the kinetic energy change due to the velocity V1 at the outlet, and kinetic energy is stored at the stagnation point, then divided by the kinetic energy is at the outlet if the flow is isentropic, which is much higher than V1, minus V01 is velocity of the fluid at stagnation point. So here inlet velocity, here velocity of the stagnation point or V0 is very small, because we are reaching the stagnation point by stopping the flow totally, and thus and find out the reach of state, which is stagnation state. I am repeating again, the stagnation state is that position where we are reducing, we are totally stops the flow of the flowing fluid and measures the enthalpy there. And what is the conditional P? What is the temperature? That is H0 and T0 is the stagnation point. But we can say we have completely stopped the velocity. If it's still not there, but velocity flow at the stagnation point is more or less equal to 0. So if we neglect it, then efficiency at eta is equal to V1 square minus Vs square. Means velocity square of the velocity at the outlet when there is uh, when there is a frictional loss of the energy or divided by the velocity of the isentropic velocity outlet when there is no loss is imagined. Now, sometimes a velocity coefficient phi is defined as the ratio of actual exit velocity to the exit velocity of the flow is isentropic. Between the same pressure, we are having V1 divided by V1 bar divided by V1 bar 1s. Velocity at the outlet when there is exit, when there is normal flow, and velocity at the inlet outlet when there is a isentropic flow. Both have bar because it's a vector quantity itself. So we can say that phi in these two equations from here and here, phi is equal to eta n to the power half itself. 1 second. Another coefficient which is frequently used is the ratio of the actual mass flow to the nozzle, omega to the actual mass flow, which will pass in the flow what isentropic itself. That is omega s. This is called coefficient of discharge, which is given as omega by omega s. Whereas the actual mass flow, the actual amount of fluid is flowing divided by the amount of mass flow when it is isentropic, when the fluid flow is isentropic itself. The convergent part of a nozzle, the convergent part of a nozzle is usually sharp, where the divergent part is usually graduated itself. What we have here, here we are deciding a convergent divergent nozzle. The angle of convergence is not exactly equal to the angle of divergence. Means angle here is not equal to angle here. If you draw a line here and make the draw the angle, and if you second draw the line here, create the angle, it is defined as, it is not exactly defined, but it is not changing at all. So the convergent, and if the semi-vertical angle is large, there will be flow separation from the wall with the foundation of eddies, which entails heavy loss. If the angle phi is small, the length of the nozzle is become too large to provide the desired exit flow area, so causing more energy loss due to friction. There is alpha varies from 5 degree to 8 degree centigrade. 8 degree, not centigrade, but 8 degree. So what we are doing here, just 1 second. Hmm. Share sound. Hmm. So what we are having here, between the divergent nozzle, the angle of convergence is not equal to angle of divergence. If the angle is weak, there will be flow separation from the wall. There will be separation of flow of the wall from all, and eddies will form. পারছি না। The convergent part, if the semi-divergent angle, most of the friction loss really occurs in the divergent portion. Means when the nozzle is area of the nozzle increasing from the minimum to the maximum itself, and convergent part, the semi-divergent angle is large. There will be flow separation from the wall, means the flow will not be completely fill up the nozzle. It will be separated from the wall itself, and there will be adhesive formation which helps cause energy loss itself. If the angle alpha is very small, the length of nozzle becomes large to provide the desired exit, causing more energy loss due to friction. So if it is large, there will be flow separation and formation of eddies, and if it is less, then length of the nozzle becomes large to provide the desired exit area, causing more energy loss due to friction itself. Thus, this alpha varies from 5 to 8 degrees itself. Next, what are the different types of nozzle available, or what's here we use here? Probably the most common physical conception of the nozzle is the converging diverging type, which, although its application in the turbine drive is somewhat limited itself. More generally, the convergent or divergent nozzles are used. Generally, we are free to do only one convergent or only one divergent nozzle, but that a turbine, we use mainly the convergent turbine we can use all right, but slowly its application is limited. In steam turbine is limited. We are using converging or subsonic nozzles. Means it is nozzle area of cross section area nozzle is decreasing from the inlet to outlet itself. Generally, this type of converging nozzle is only two types: rimmed or round nozzles. Rimmed means there may be certain helix or remersed helix inside the nozzle so that the flow gets a circulation revolution and increases. And then foil nozzle, there will be certain foils inside the nozzle which is kept inside to control the direction of flow of the fluid itself. The rimmed nozzles or nozzle with some helix with the formation of helix, screw helix inside is generally used in the high pressure impulse turbines, where we have a very high pressure, and by using the nozzle we can redirect this very high pressure from the inlet to outlet to a considerable extent, so that this high pressure is converted to high energy velocity for injection in the turbine blade itself. The principal advantages of the rimmed nozzle are it is a low cost, is a manufacturing adapted to standardization, because you can safely in a tapered nozzle area you can safely make one helical thread like substance with an helix approximately 40 degrees or so, and this comparatively low cost is their cost is less in case of the non-rimmed helix. And the principal advantage of the rimmed nozzles are low cost, ease of manufacture, and adaptive standardization. So manufacturing is less, that's why cost is also less, and adaptability to standardization means we can make a standard. Say that should be the standards of the helix inside the standards of the helix angle inside the norm, and we'll follow these helix in the case of preparation and will not go something else. So we can, so in manufacturing, we can make only a certain few standard helical nozzles, and there you can go for mass production itself. Now, the principal disadvantage is efficiency is comparatively lower. Means there is more heat. More heat due to friction is created, and thus there is more heat loss from the stagnation to the outlet of the velocity itself. And length is somehow to make it up to a certain greater length, because unless we have the helix up to a certain length, this will not create our necessary principal production, and enable it to utilize effectively for low purpose area for a given flow analysis. The angle of divergence is rimmed nozzle, as mentioned earlier, is usually about 12 degree and rarely above 15 degree. Rarely, the angle of divergence which we have, it is rimmed nozzle, you see, rimmed nozzle high pressure and or subsonic nozzle, two types of nozzle. The angle of convergence is rimmed nozzle is somewhat high, comparatively higher, say 12 to really over 15 degree. In order to avoid flow separation with this attendance less, the convergent part is normally sharp, and a good fillet or round entrance is provided. So here what we are doing for the rim foil, we are not strictly following the convergent type of nozzle, but we are using divergence with comparatively higher degree of divergence, and to avoid the flow stress and the attendance loss itself. The convergent parts is normally sharp, and good fillet or round entrance is provided. The foil nozzle is formed by curved airfield section. Is formed by curved airfoil section. The nozzle is short with well-rounded entrance edges, and sharp exits according to a good issuing jet itself. Now, foil nozzle is formed by curved airfoil section. Airfoil means what will be the foil of air in case of the convergent itself. It's like a aircraft blade. Is that type of airfoil itself. This nozzle, if we if you allow the nozzle to flow through this airfoil itself, its airfoil will control the energy. It's called energy considerably in order to increase the velocity of the output itself. The nozzle will be short in length, unlike the rim nozzle, uh, and is with well-rounded edges and sharp exit edges according to Lute issuing jet. Means here all the edges of the foils should be well-rounded. There is not sharp, and but exit it will be of sharp. At the inlet it is well-rounded, and at the exit it is entrance edge it is well-rounded, and exit edge it is sharp according to good issuing jet. This nozzle are very high efficient, costlier. A foil nozzle block A foil nozzle block is made by welding the individual foils between the section of the concentric rings. A foil block is made by welding the individual blocks between sections of concentric rings. The block is then welded in place between the outer and inner shroud. The foil nozzle finds wide application in large steam turbine itself. So what against this made of welding individual? First you have to make the foils according to our design, and then you have to fix it foil inside the nozzle by means of welding and between the section of concentric rings. The rings should be concentric nature, means it should have we should have the fixed few rings and fix them few rings, and rings are placed inside the foil and welded there. The block is then welded in place between outer and inner states. From the outer and inner, there is a particular position. We have to sit these blocks and do it. The foil nozzle finds wide application generally in large simple turbine because it is converting the very high pressure into a very high pressure stream into a very high velocity stream itself. Now, let us go to the flow area of the nozzle. If the condition of flow stream at inlet to the nozzle is known, the critical pressure can be estimated by multiplying the inlet pressure P0 by 0.546 or 0.577. So, if we know the condition of the stream at the inlet, the critical pressure can be estimated by multiplying the inlet pressure P0 by 5.46. And we know what is the critical pressure. The critical pressure ratio, and now we know what is the critical pressure. The discharge when M is equal to 1 means M is flowing according to the velocity of sound. At throat it is equal to 1, the discharge is maximum and the nozzle is said to be choked. So when M is maximum, we have the highest velocity of stream equal to the velocity of sound, and discharge is here. There is a maximum. Nozzle set here. Discharge is maximum as the nozzle is defined, and nozzle is defined as being choked. So the condition of the nozzle is known. The critical pressure, and it is incapable of allowing more discharge even with further discharge critical pressure. This discharge is known as critical discharge properties that is throat under this condition are called critical properties and added by the superscript asterisk. So in a convergent nozzle, the velocity at the exit from the nozzle is sonic, and where the velocity at the maximum and the exit properties are critical properties. That is substituting them. So the ratio of the temperature at the throat when the velocity is there in some sonic T to the inlet temperature T0 is called critical pressure. When the throat velocity is equal to the sonic to sonic equal to the temperature sound, then this pressure, the inlet temperature defined T0 is called the critical inlet pressure itself. Inlet temperature. Now, the critical pressure can be estimated by multiplying the inlet pressure P0 by 0.547 or 577. So inlet pressure we are increasing around 150 times, depending on whether the inlet stream is superheated or dry saturated or superheated or dry saturated, respectively. If the exit pressure is given, the nozzle efficiency is known, and the exit velocity of the stream as well as the exit critical velocity of the stream at the nozzle can be estimated from V1 is equal to 44.72 H0 minus H isotropic multiplied by efficiency of the nozzle, and whole this item within the bracket is under square root, which is at V star, the velocity of the flow at the critical portion is equal to 44.722 H0 into Hs is temperature of the enthalpy of the flash at the critical position multiplied the efficiency whole to the power square root 2. Now, what is this going on here? We are getting two velocities, the exit velocity of strain as well as critical velocity of the steam. Exit here as estimating as a factor given as numerical factor 44.72 multiplied by the difference between the saturation between the difference between the stagnation ratio, difference between the enthalpy at the stagnation point minus enthalpy at outlet when it is fully saturated itself, and then V star is the velocity at the stagnation point itself, and at the critical point itself is given by 44.72 multiplied by H0 minus enthalpy at the critical point, critical enthalpy, multiplied by the efficiency of the nozzle itself. So it is brought to a limit which is actual, but enthalpy H1 at outlet is not equal to H1 star. It is not critical velocity. Critical enthalpy is different. That's why you put the value of H star, HS star to index of H2, and thus by square rooting it, multiplying it by efficiency, and then square rooting it, we are getting that result critical velocity as well as actual velocity of the throat itself. Here, enthalpy drop P0, H0, H1 are taken care from the Mollier chart itself. With the actual state of stress at exist and the throat being fixed on the Mollier diagram, specific volumes can be estimated from it. The actual stream of fluid exists and the throat being fixed on the Mollier diagram, then specific volumes can be obtained from it. Volume per unit mass we have to obtain from it. Now, knowing the mass flow rate of omega, the flow requires at the nozzle exists as well as at the throat can be estimated from omega is equal to A star into V star divided by V star. So, cross-section area at the critical point multiplied by the velocity at the critical point is a vector, and velocity divided and the velocity V, or A V1 dot is equal to A1, and A star omega V means the nozzle tubular cross-section, the rate of flow of the steam through the nozzle is given by omega itself, and V is the velocity, is the specific volume of the moving fluid. With nozzles are circular in cross-section, A1 is supposed to be pi by 4 pi by A multiplied by D exit. Multiplied by D exit means D square exit means square of the diameter of the nozzle at exit itself. So, which means we are getting the area at the exit and multiplied by the efficiency itself. So, get is this, if the nozzle then circular in cross section, we can follow this process. Whereas the number of nozzles and exit is the exit diameter of the nozzle. The exit cross section may be rectangular or square also. Foil type nozzles are mounted in a nozzle diaphragm, which is horizontally split into two halves and joined by a vertical flange bolt at the bottom half. So, foil nozzles are mounted in the nozzle diaphragm. It's nothing but a frame over which we have to fix the nozzle by screwing, and extremely split by into two halves, split into two halves and joined by the vertical flange bolts. It is that flanges which carry the nozzle is joined from the bolt from the outside, and the top half of the diaphragm, which forms the status, can be lifted by cranes and just exposing the rotor for inspection, and inspection is needed. So what we have in the nozzle diaphragm, this is the nozzle diaphragm. It is made of foils. It is screwed within this diaphragm itself. Here, it is the same in the top. where same in the top where you can fix the bracket itself. These are the flange bolts where you fix these two flanges so that the flanges can be opened and cleaned, inside can be cleaned or inspected according to repair if needed. And this is the foils which used in the foil type nozzle, where this is the foil itself, which like a aircraft blade, and eta n is that same efficiency is depends at the eta n itself. And dm is the maximum mean diameter of the nozzle diaphragm, mean, and the height of the nozzles and breadth of the mass as the on the mean diameter itself. Now, if dm is the mean diameter of the nozzle diaphragm, hn is the height of the nozzles, means what is this? Eta is alpha is the angle between these, t is the angle, t is the o is the distance, p is the pitch of the nozzle on the mean diameter. How many nozzles are kept on this diameter itself? That is pitch, and a number of b is the number of opening for flow. If phi is the number of opening for flow, so how much nozzle we have to calculate, that you have to know. Okay, and t is the thickness of the nozzles, and n is the number of nozzles. And a as a cross section at nozzle for angle, alpha at nozzle angle is subtended by the nozzle axis with the plane of rotation by the wheel itself. When the maximum area of nozzle open for stream flow, an is equal to 0 into hn into n. So alpha is the nozzle angle, angles up to nozzle axis, and the plane of rotation of the wheel, and the maximum area of nozzle open is for stream flow. Maximum it can be h0 into n. A1 is the cross section, which is the maximum cross section which we can allow by means of nozzle by controlling the position of the nozzle itself. Now, what is sigma is equal to p into sin alpha becomes 0, and rho into n is equal to rho into dm by n. An is a p sin alpha minus t into hb dot pi into dm by p, pi into dm hn into I sin alpha into 1 minus t by p sin alpha itself. So pi dm hn sin alpha plus km, and where km is the nozzle thickness factor. So what is the d? Dm is the mean diameter of the nozzle itself. Hn is the enthalpy at the inlet. Alpha is the angle of the nozzle, the horizontal, and km is the strength factor itself. So area of the nozzle, minimum area of the nozzle which is supposed to open is available from this equation itself, which contains an, which is given, taking into consideration the H0, enthalpy at the stagnation pressure, number of nozzles, and then the angle of the nozzle with the horizontal itself multiplied by the pressure rise minus 1 into n pi dm by 50, and area of n is p sin alpha minus t into H0 into pi dn by 50. We replace the value of pi itself, and Hn is the H0 is here again. P sin alpha minus t is the thickness of the nozzle, pi dm, and the mean diameter of the nozzle itself, thereby internal pressure created. So after certain addition or subtraction with dm's, pi dm H0 is into sin alpha itself. This p and p is subtracted, and minus this is t divided by p sin alpha itself, and this factor 1 minus t by p sin alpha is defined as a nozzle coefficient factor itself. Okay, let us finish this class here.